generation from green ammonia. Three topics, they are not correlated. Hydrogen generation from green ammonia, that's what I'm going to begin with. And also the other is ammonia as a hydrogen carrier and storage. I think it's the same thing. So when you use ammonia as a hydrogen carrier, you have to decompose or turn it back into the hydrogen. So I'm kind of combine this both, but so that's okay. The third one is a challenge and solution at a plasma and plasma solid interface. So that's one. I think the third session today, I'm going to focus on that one, plasma water, also the plasma solid. But I'm going to combine hydrogen generation from green ammonia and also ammonia as a hydrogen carrier. The whole idea is ammonia hydrogen carrier is you carry hydrogen, you got to decompose, and then generate hydrogen again. So it's the same thing. I think there was a lot of confusion putting this topic together, but I would try my best. Okay. So let's get started. Let me know when you see the slide. Can you see the slide?
Yeah, yes, sir. It's visible.
Okay. So actually, the slides I'm going to present in this session is the one actually I just presented at American Institute of Chemical Engineer annual meeting in San Diego last month. So now I'm going to present here. So actually the perfect timing. So I think looking at the renewable, we talk about the renewable energy, right? So when you produce green ammonia, you have green electricity. So basically, this is cartoon tells you turn green energy into the green ammonia, then you decompose and produce hydrogen. So then hydrogen can be utilized for different application, right? So you can directly use ammonia. But regardless, we already in the last 5 days we talk about how difficult to make ammonia at a low temperature, low pressure using unconventional way. So Haber-Bosch process has been going on for over 100 years, using microwave, electrochemical, and plasma, low pressure. It's a challenge, but true. That's the way to go, right? Because you have to utilize the renewable energy. So the bottom line is this direction. If you look at, let me get if you can see my circle. So the bottom line, if you have this nitrogen and hydrogen from ammonia, the reaction is equilibrium control. That means it's going back and forth. So my research focus on ammonia. So we make ammonia. So now today I'm going to talk about how are you going to decompose ammonia or the generate hydrogen from the ammonia. So what's the challenge? It's difficult to go from the left to right, right? Hydrogen plus nitrogen to ammonia, but actually the decompose ammonia back to hydrogen is not that easy, depending on the purity of the hydrogen you want to produce. Okay, so that's the topic. This session is the hydrogen generation from green ammonia. So keep in mind, ammonia synthesis is exothermic. So that means decompose ammonia is endothermic. Is that right? Because basically from ammonia to make it is endothermic. That means you have to give the heat. So what's the challenge? The challenge is to produce 100% ammonia at a low temperature. So if you produce for endothermic reaction, the higher the temperature, the better, right? The higher temperature, the more equilibrium going to the right. So the challenge is that if you want to make 100% conversion at a low temperature, that's a challenge. So my question is, for application in certain area, such as the fuel cell, if you turn the ammonia into the low-grade hydrogen, it's fine. You can keep ammonia in there. But for certain application in fuel cell, you are not allowed to have ammonia to present. That means this reaction has to go all the way to the right, no ammonia present. So my question to the audience, why for fuel cell application, let's say if you have ammonia and you want to run a fuel cell, I'm talking about hydrogen fuel cell, you have to decompose, basically you have to decompose ammonia first within the cell or outside the cell, fuel cell. Why you have to achieve 100% conversion or 99.9% conversion? Can anybody tell me what if you have ammonia in hydrogen fuel cell? Just give it a try. What's going to happen in fuel cell? Have you ever heard of a PAM fuel cell?
Yes, sir.
So basically, what's going to happen? I'm going to write it here. PM fuel cell, okay. So what's the poison of the PAM fuel cell electrode? We all know it's a CO, carbon monoxide, all right? So if your hydrogen should not have a CO. If carbon monoxide is greater than I forgot. So I used to work on, maybe I would say 1 ppm, and your electrode will get a poison. And what will happen with ammonia? How ammonia is going to poison the fuel cell? Anybody give a try? It's corrosion, all right? So what's in the fuel cell? Your fuel cell has a lot of the electronic, all right, copper or something. Ammonia, they basically interact with a lot of joints, and then if you have ammonia feeding the fuel cell, I'm not sure if ammonia will poison the same way as carbon monoxide. Because carbon monoxide really attack the platinum electrode, but ammonia will go and look for anything copper. This is the reason. Even if you are the mechanical engineer, have anybody using the ammonia cylinder? What's the regulator you use? This question. Anybody answer me? Have you ever used ammonia in your laboratory? What's the material made of regulator? You have gas cylinder, all right, or the ammonia cylinder. You have a regulator, all right. Commonly, that regulator made of brass or copper. Can you use that regulator for ammonia?
Basically, it's iron only.
What do you use?
Well, yeah, basically. Yeah, basically it's iron cylinder only, but I think there is some
it has to be, yeah, it has to be stainless steel. Okay, so you basically if you go to any chemistry laboratory or even mechanical engineering laboratory, any gas cylinder, hydrogen, nitrogen, whatever you name, it's basically the material. If you look at the regulator, one gauge on indicated cylinder pressure, the other delivers gauge. All right, they are all made of the copper, give or take. It doesn't matter in India, in China, in US. Most of them are made of brass because it's cheaper. Now for ammonia, you have to use stainless steel. That's the reason. So that's why ammonia interact with the copper or the brass. Okay, so that means anytime you have a fuel cell, ammonia will go in and then basically make a corrosion fuel cell. So what does that mean? So if you have a hydrogen PAM fuel cell, try to utilize. Let me put it this way. So you have a fuel cell, you need hydrogen, all right? So ammonia is a hydrogen carrier. So this ammonia made 1,000 miles away, it transported to the place where you have fuel cell. Now you have to turn ammonia into hydrogen in order to run fuel cell. So that hydrogen here can only contain nitrogen. You cannot have ammonia left over. So that means it has to be 100% conversion. You understand what I'm saying?
Yes.
Okay.
Yes.
Yeah, I want the audience to, I don't know how many the microphone you have, so I would like to audience if you have, if the next week, this is the first week, today is day 5. I think we have 5 more days to go. So I'm trying to make a suggestion. If you can, please have a couple for the microphones, not just one. Give to the the several students. When I ask question, I would like the student just say yes or no, so I can continue. Otherwise, I have to pause here because I ask question, nobody answer. So anyway, so I want to make sure. Okay, everyone, you have a couple of microphones if possible in the in the classroom from Monday. We still have 5 days to go. Today's day 5, so day 6 to 10. If you can request several microphones, I would be really appreciate. Um, so anyway, so that's why you understand, all right? So the ammo ammonia synthesis, which means hydrogen plus nitrogen, you do not need to get 100% conversion. The reason being that you have downstream separation and then the hydrogen nitrogen recycled. Now, talking about the ammonia as a hydrogen carrier, when you deliver ammonia to the site for use, especially for the fuel cell, and then you have to do 100% decomposition, which is a challenge because keep in mind this endothermic reaction and also the require high temperature and also this reaction is very difficult to do go 100%. All right, so it's a challenge to decompose ammonia. So what's the solution here? So that's the focus today. So basically, if you want to decompose ammonia, keep in mind you need high temperature, all right? But high temperature costs energy, all right? So we basically, again, for the ammonia decomposition at the West Virginia University, we use same technique, microwave. We just don't do the synthesis, we change the catalyst, and then we decompose it. And so the catalyst we use called the monolithic. Anybody heard of a let me write. Anybody heard of a monolithic catalyst? You see, this is 2 dimension. But the monolithic, have anybody heard of monolithic catalyst? If you drive a car, what's in your car? It's called catalytic converter. All right. So those are monolithic catalyst. It's a structured catalyst, have the regulator the structure like this, where you can put a catalyst onto it. So what's the reason we use a structured catalyst like this? There's a reason to do that. Okay. So because we want to save energy, it's a selective heating. We use this structure and then we can start heating this active site. So this imaging shows you thermal imaging how you see on the catalyst surface there are by the way, the thermal imaging basically is like this. You heat the monolithic catalyst, and then the hot area shows the red color. It's just the red color means high temperature, and then the blue color means low temperature. So you can tell there are hot spot formation on the surface. See, this is on the left hand side. See, this is number 2, 3, 4. Those are those hot spots. That's what we want. So it's a non-uniform or selective heating. So the whole body of this monolithic structure is not really hot, but the site is very hot. Keep in mind, the reaction happens on the active site, not on the body of the reaction. The body only provides infrastructure or surface area, all right? So we use the active, we decorate the catalyst on the monolithic structure. Then we use microwave to drive. So the structure can be, I would say, maybe 400 degrees C, but this active site can be 600, 800 degrees C. So that means we can have a localize the hot spot and drive this endothermic reaction. So that's the design of the catalyst. I'm going to pause here. Anybody have any questions here? How we design the catalyst and then to do the ammonia decomposition reaction? So this is this is monolithic catalyst. So we basically have the catalyst that are sensitive to the microwave, so then we can heat it. So, but you still have a channel. This two-dimensional, basically gas flowing through. But you want to have a channel, and then doesn't create a pressure drop. This is exactly the structure, a catalyst you use in your car. If you look at your car, you have catalytic converter. They are the design concept same. They loaded with different catalysts. So, but in here, in ammonia catalyst, in the rest of the slide, I'm going to show you how we design this the active ingredient so they can basically decompose the ammonia under microwave very fast. So this is one of the design. Another design is on the structure on the left-hand side. This is called cold shell design. Anybody heard about cold shell catalyst? Cold shell catalyst? Anybody heard about the cold shell catalyst? It's just the picture shown here. Basically, this is cold shell catalyst.
I'm not aware of it.
Okay, so nobody aware of the cold shell catalyst?
Yes, sir.
Okay, so now let me spend the time interpret. Okay, so cold shell catalyst is very useful for the microwave catalysis. You see, the shell is a catalyst. Okay, the core is called a susceptor, microwave susceptor. That means the core is very sensitive to the microwave. So that means the microwave will heat the core, and then the core become very hot, then heat the shell. This is different from conventional heating. Conventional heating, you basically the heat coming from outside, and then you heat catalyst, the core is not heated. On purposely, when we design the catalyst, you have core which is the microwave susceptible. That means very sensitive microwave. We heat core and the heat transfer direction is going this way.
Understand.
So this is heat transfer direction. Make sense? So basically, microwave, but let's call that. I'm gonna draw the microwave. Okay. So basically, when microwave come in, oh gosh, this is not the correct one. I'm gonna kill this. Got stuck in here. Okay, so all right, I try to draw something make sense. So basically, the microwave coming in, they go directly inside here, and then heat it up, and then the heat generated from inside and radiate outside. But heat radiate outside. Remember, the microwave is a field, all right? So there's a field of microwave. It's called a microwave coming in, and then the heat core, and then the heat transfer from inside out. What's the advantage of this heating the mechanism? So think about this. If you have ammonia coming in, and then the core is heated, all right? So the ammonia interacted with the catalyst surface, and then the heat transfer direction from inside out. So that means the delta T is from inside out. If you learn the what you call that, the chemical engineering transport, so the diffusion of the molecule is driven by two things. One is the delta T, the other delta C. Delta C means concentration. That means if one molecule if the diffusion direction means from high concentration to low concentration. Makes sense, all right? So that's common sense, but you don't have to learn chemistry. You will know this because molecule will from high concentration go to the low concentration. That's a diffusion direction. Molecule will, I'm talking about gas molecule, will diffuse from high temperature to low temperature, all right? Because they try to push the direction. So by heating from inside out, first we heat a shell, catalytic reaction taking place. So once the ammonia decompose and form the hydrogen on the surface, H2 and nitrogen, immediately, because the heat transfer is from inside out, the moment the ammonia decompose and to form nitrogen and hydrogen, and then the heat transfer push them out. So this is very fast kinetics. The reaction is very fast. That means there's no chance for hydrogen and nitrogen to recombine to form ammonia. The moment they form hydrogen and nitrogen, and the heat push them out. So that's why this is the way to basically you have to take advantage of kinetics in order to fully decompose the ammonia. Otherwise, if ammonia and hydrogen and nitrogen stay on the surface, they are going to reach equilibrium. They are kind of bouncing back and forth. Okay, so this is so-called non-equilibrium operation. Non-equilibrium operation means my surface is never reach the constant temperature. There's so many hot spots. That means even if you can measure average temperature, however, I have so many hot spots. That means locally they never reach equilibrium. There's so many localized equilibrium going on in here. But the moment ammonia decompose, I push the molecule to the push our molecule out. So this is so-called non-equilibrium operation, so that we can achieve 100% decomposition. And also ammonia decomposition is the endothermic reaction. You have to make sure you provide enough heat. So that's why one catalytic design is we have so-called cold shell design. We heat the core and then put a shell. The other design, we take the commercial structure, the catalyst like you have in your catalytic converter. Then we put a microwave sensitive catalyst into different locations, just like this picture show, and then we heat selectively. There are different ways to design the catalyst, but the whole idea is we want to have faster kinetics. So I'm going to stop here a little bit. So anybody have any question? I heard somebody try to say something. Any question about the catalyst design? Does it make sense to you, or you got confused?
Yes, sir. We understand core cell catalyst. So in that picture, which is showing the reaction rate, red and yellow, blue color indicates.
Yeah.
That we are not understand fully, sir. We understand heat transfer phenomena in core cell catalyst, but we can't get that contour, sir.
Okay.
Plotted contour.
All right. So basically this is the imaging. It's called the thermal. Okay. Let me show you. Okay. This is how we do experiment in my laboratory. Did you see this is the thermal camera? So this thermal camera actually basically the pointing to the reactor tube and then to the catalyst, and then the catalyst. Let me draw the picture for you. Okay. So basically, the thermal imaging really watching this is the surface. I'm going to draw a cartoon for you. Let me see what's the best way to draw this. Okay. Yeah, you have to know our monolith. No, it's not here. I think I have a cylinder. There should be cylinder shape. Okay, here we go. So this is monolithic catalyst. Okay. So this is exactly what you have in your catalytic converter. It's a cylinder shape. And then on the top of surface, let me go to. So this imaging here, if you look at my circle, it's the top of surface here. You follow me? So that, because there's a channel. So gas, if you have gas, the ammonia will flow this way.
Yeah.
Okay. So this ammonia will flow this way because there's a channel. So basically I'm not very good. So if I put this two-dimension, the two-dimension is really the top surface. I would say the top view of monolithic. So now when basically the channel, is that right? Because it's a monolithic, there are so many channels in there. So we basically decorate the catalyst on the surface. And during reaction, we also put camera here. So this camera also watching this way. And that's the image. Why you see I draw the nicely, but actually monolithic cut is not, when you cut it in a laboratory, it's not like perfect cut. So that means we decorated the certain cell, but some cell may not be decorated. So you can design this the structure. They are not microsensitive. We only have this is the coated surface. This is the orange dot. They are microsensitive. This is energy saving. You don't want to waste energy on this block. Catalysis doesn't happen on the block. Catalysis happen on this the active site. You know what I'm saying? To save energy, you really want to heat this selectively. You follow me? So otherwise, it's endothermic reaction. Keep in mind that the key word here is endothermic reaction. The reaction needs a lot of heat. But if you heat, your objective is to heat at the active site. But don't waste the energy or the heat. Don't waste the heat on the monolithic structure. The monolithic structure is just a place or template hold your catalyst in there. Follow me? So this cartoon really is not perfect. Let me show you a good one. I think there's, yeah, this sometimes I think we are looking for this the right spot everywhere. Let me see this one. This one is okay, but it just depends on how I would say probably every 10 seconds. And then okay, this silicon foam really tell you the story. Did you see this silicon foam? It's not perfect or a square shape, but that's not. Hello, can you hear me? Looks like my internet is not stable. Hello?
Hello. Yes, sir.
Can you hear me?
Yeah, now you are audible, sir. You are audible.
Oh yeah, because it shows a warning saying my internet is not stable, but I can see my internet is okay. So I want to make sure you can hear me, all right?
Yeah, you are audible, sir. You are clear.
Okay. So all right. So this monolithic is not, in reality, it's not perfect. In reality, this monolithic is cylinder, but it's actually, you see this? It's like this. But in laboratory, but in industry, they can make perfect. If you open your catalytic converter, it's perfect because they can machine very well. But in laboratory, it's only like 2 centimeter. We have to take the commercial bigger one. We in laboratory we have to cut it. So, but the point I try to make is the whole idea is we don't have to heat the whole thing. We want to heat the catalyst that are decorated or coated inside the porosity. And then you can see the temperature. The thermal imaging will tell you the temperature. We look for the hot spot. That's how we want to drive the reaction. Understand? Make sense? The design, the catalyst design concept.
Yeah, yes, sir. That in slide number 3.
Yeah.
In slide number 3, left side images. I mean that left side contour is indicating core cell catalyst, or that also monolithic catalyst.
Yeah. So the picture the picture was taken at different time. These are two pictures. So the picture is top view using another camera. This is the thermal camera take it, right? You see there's a little window here. See there's a thermal camera. This reactor, if you pay attention to it, there's reactor tube in here, and then this cylinder, this one is just sitting here. You see what I'm doing? So this is cylinder shape. I put it inside the tube, and then the camera take it. We can also take the imaging from the side view, but the whatever picture I show you is this cylinder put inside the reactor, and then the camera taking the top, because we want to see the distribution on the radial side, temperature distribution on the radial side, which is on the surface. See if uniform. The two pictures are taken at different time. So, and then the whole idea is we want to see a lot of hot spots on the surface, just show like this, and then that drive the reaction. But the remaining, all this blue shows the body is cold. Only the hot spot is hot. Okay. The whole idea is the catalysis happen on the active side, and then we want the majority of the support being cold, but the only hot spot. So that's energy saving, because if you heat this block, that's a lot of energy spent. So this is the beauty of the microwave. They can slightly heat. If you use conventional heating, I can guarantee you the whole thing will be red color. I mean, if you use conventional heating, radiation or the conduct heating, the whole picture will be the red color. But with the microwave heating, we only heat this active side.
Yes.
This design concept. So, and then by the way, this is 3D. This can be 3D printed or can be cut from commercial block. So there's, if you look at a schedule, there's a session on purposely I skip that session called 3D printing. 3D printing, you can print anything, but I want to save that 3D printed catalyst, which is supposed to be on the day 3 to today, because you have to talk about the 3D printed catalyst along with the reaction. Otherwise, if you print the 3D just for fun, you can print a toy for the kids. But I want the 3D printing catalyst makes sense. To illustrate, you can print a perfect 3D printed catalyst cylinder shape, and then today. So, but unfortunately, on the picture here, I show you this is the one we cut it using machine, because a silicon carbide we couldn't find the good ink to have silicon carbide, but alumina silica you can print perfectly. But silicon carbide we have to take a foam and using machinery machine it, because silicon carbide we want to make silicon carbide is microwave sensitive. We want to put in the core and coat it on a shell. So the different reaction mechanism. Here is decoration inside the channel or monolithic. Here is the so-called cold shell. It's different design, but it's all take advantage of the microwave selective heating. Make sense? Understand what I'm saying?
Okay. Yeah. Yes, sir. Yes,
okay.
Sir.
So okay. So this is the design. It doesn't matter you do the 3D design or you do the so-called the monolithic. So this is where you design the catalyst. You have to make sure what reaction going on is endothermic. Endothermic means you need a lot of heat. So that means in the terms of engineering, if you're dealing with endothermic reaction, you want to be careful. You want to deliver energy or deliver heat on the active side. Do not waste energy. That means do not heat some parts you don't have to heat it. So this good. This is advantage of the microwave. If you use conventional heating, remember this monolithic has to be inside the metal reactor. The metal reactor will release a lot of heat, waste a lot of heat. So microwave doesn't. Microwave just heat selectively. Anyway, I'm not going to waste my time. If you have any questions, just let me know. Otherwise, I'm going to show you the data. Okay. So keep in mind the challenge of the ammonia decomposition is not just a reaction. It's a 100% decomposition at a lower temperature. Okay, so you want to save the energy. Yeah. Okay, so this result, I'm going to spend a little bit of time to interpret it. First, we have this silver oxide using iron catalyst because iron is cheaper. All right, the Haber-Bosch the catalyst is iron-based catalyst. Now, The reason we put the iron on the silver oxide is because silver oxide as a support, they have electronic property. Remember yesterday we talked about the what's important of the feature of the catalyst support. It's not just surface area. For certain reaction, surface area of support is important, but for ammonia synthesis, the surface area may not be as important as electronic property. Remember yesterday we compared the magnesium oxide, silver oxide as a support. Even if their surface area or pore volume are different, but their electronic property are important. So now when we try to select the catalyst, so-called active ingredient, to be coated on the monolithic, we have to do the powder testing. Powder testing means it's ingredient. Okay, so we eventually the next couple slides we want to coat the powder on the monolithic, and here we want to compare iron on the silver oxide. So in terms of the ammonia decomposition, it's very similar to the ammonia synthesis because you need promoters. So this is on the left hand side, it's called ammonia conversion, and then we start with the iron on silver oxide, then the potassium promoted with the potassium on silver oxide, and cesium and iron. So keep in mind for ammonia synthesis is a base catalyst reaction. Base catalyst reaction means your catalyst has to be electron donor. Okay, so that means alkali in the periodic table, the first row or the first column is important. So you have very few people use sodium. It all begin with the potassium and the cesium. So those are very good electron donor. So we want to compare potassium, cesium, which one can promote iron based catalyst. So that's the idea for the, I would say, the powder catalyst design. This even before we put on the monolithic. Okay, I give you such a, I spent half an hour to discuss a design concept on the monolithic. Now we back to active ingredient, which is iron on silver oxide, which eventually will be coated on the foam or monolithic structure. Okay, this is another way to design the catalyst. So we do the powder. It's called screening test. This blue line shows the iron on the silver oxide. So without promoter, if you have a potassium promoter, and then they basically going this way. So you can see without promoter, by the way, this is a temperature, and this is ammonia decomposition. So our target is to see at what temperature they reach 100% conversion. Keep in mind, the lower the temperature to reach 100% conversion, the better the catalyst. You follow me? Because we want to save energy. So if you look at the iron-based catalyst, and then you heat up the catalyst only until 350 degrees C, the reaction start taking place. Even the reaction start taking place, it can struggle until they probably reach 450 to 500 degrees C. The last data point is not 100% conversion yet. It has to keep on going until 500 degrees C to reach 100% conversion. But our goal is not to hang up with this iron catalyst, because our goal is to see which promoter is good. If you look at this promoter potassium, it takes 350 degrees C. At the beginning, it's almost linear going on. Again, for the cesium, it's linear and then started going on. It is really the last mile or last the couple conversion takes a lot of effort, but eventually both reach the 100% conversion. So you may be wondering that why we choose the cesium and potassium, or is it because we are just so lucky and then we choose these two? Actually, not. If you remember, cesium potassium in the yesterday is a promoter for ammonia synthesis. It's the promoter for the forward reaction. We have a reason to choose for the reverse reaction, and then because if you remember, catalyst does not change the thermodynamics, but catalyst will speed up the forward and the reverse reaction to reach equilibrium. Follow me? So that's why the promoter, that to speed up the forward reaction, it should speed up the reverse reaction to reach equilibrium. So that's what we have. There's a reason when we design this formula. So now same thing when you see the hydrogen production. Of course, when you reach 100% ammonia conversion, you will get a lot of hydrogen coming out. So these two curves should be imaging. One is the ammonia conversion. When you reach 100% conversion, if you do the calculation, the hydrogen here, in theory, should be theoretically the highest amount of hydrogen you can generate because you decompose the ammonia. Ammonia decomposition will not go anywhere but hydrogen, nitrogen. Okay, make sense on this one?
Yes, sir. Yes, sir.
Okay, so let's go to the next. So now we have a very good powder. We want to say, remember our goal is to put on the monolithic. There are two reasons we want to do the monolithic because the pressure drop. When you decompose the ammonia for hydrogen production, keep in mind your downstream is the fuel cell. We want the hydrogen to go to fuel cell. So that means the gas flow very fast. When gas flow very fast, the pressure drop is high, all right? Is related to linear velocity. So that's why we have to choose the so-called monolithic catalyst and then the flow fast. If you choose the so-called powder or packed by the catalyst, and then there's so much pressure drop, we cannot finish the reaction. So this reason I'm pretty sure when you drive a car, I'm talking about gasoline or diesel car, not electric car. In the back of your car, underneath there's a catalytic converter. The catalytic converter is designed when your engine combusts and the exhaust gas come out, they need to take out the NOx and SOx. All right. So the NOx coming out, they should not be passing through the catalytic converter. That's all. However, think about it this way: if your catalytic converter got plugged, what's going to happen? If your catalytic converter getting dirty, getting plugged, what's going to happen?
So when we are cutting that automobile catalytic converter.
Yeah. So if you drive your car, just say somebody block your catalytic converter. Can you drive? Your engine will stop, all right? Because your engine combusts. Exhaust gas has come through your catalytic converter. If somebody block you the exhaust, your engine will start combustion. Makes sense because pressure build up. Is that right? Correct?
Yes, sir.
So to say different way, you cannot drive in the flood. So let's say if you drive into the water, and then the moment the water, the level passing through the level of catalytic converter, your engine stops. Why? Because the pressure build up. Your engine pressure will not push the gas through. Same with the reactor. So if you go monolithic, build up the pressure, and then it will not allow the gas ammonia passing through, your reaction stop. Make sense? So that's why the pressure drop is very important in any catalytic converter. Doesn't matter chemical plant or the refinery. You have to minimize the pressure drop. When pressure build up so much, you have to shut down your reactor. Otherwise, all kind of reaction happen. That's why I use your car as an example because your combustion engine does not produce too much pressure to fight with your catalytic converter. The moment catalytic converter got clogged and build pressure, your engine give up. Okay, so same with the reactor. Okay, all right. So now we have powder, but we cannot run the powder for decomposition because the pressure drop. So we have to put powder on the monolithic support. All right. So now we put this powder on the silicon carbide support. We put this powder on this silicon carbide foam. It's monolithic, and then you see that it's such a porous material, and the gas can flow through. If you put a powder, nothing will flow through. So we put powder on this one, and then we know that powder is active, all right? So we put an iron-based catalyst on it again. This time we know, remember we know during the testing of three formulation, iron, potassium iron, and cesium, we know cesium the best, right? The powder. So okay, we choose cesium on iron and then coat it on silicon carbide. So this is testing. Okay. So now, so basically when we do the cesium testing, we basically run this. I would like you to look at this coated silicon carbide. We basically tested, let me see, cesium iron and then cesium ruthenium. So now we change the catalyst. So these are two different catalysts. So both on the monolithic. So the cesium iron is cheaper, and then but the iron is slow compared with the ruthenium. You see this is ruthenium, this is iron, and this is ruthenium, and this is iron. Cesium. So that means if you basically this different comparison. We change the formulation. We also put on the support because we know cesium is good. Only thing we do not know is either iron is good or ruthenium is good. So we fix the cesium and then we change it. We compare iron ruthenium. So ruthenium is better now. Okay, make sense? So the last one. So I think before I end this session, and then I want to show you this is the final result. So first, we know cesium ruthenium is good. Okay. Let me try to repeat. Based on this study, we know cesium as a promoter is good because we fix the iron and then we change a different promoter. Is that right? Cesium is good, but we don't know if the iron is good or not. Let's change it to another metal, which is ruthenium. Then we found out cesium ruthenium is the best. So we take this formula, cesium ruthenium, and then here's the comparison. Okay. So what we did was we basically run the silicon carbide blank. Want to make sure silicon carbide as a support by itself does not have activity. So if you look at the blue line, it doesn't have any activity to decompose. It's zero. Ammonia conversion easier, which is good. That's blank run. Now we go ahead to run the cesium coated catalyst, which is this blue bar. And then we run the cesium and the ruthenium on silver oxide non-coated. It looks better, right? But keep in mind, we load the same volume of the powder versus the silicon carbide. So what does it mean? Although this black line, cesium ruthenium non-coated, looks active than the coated, but they have so much material. This is powder. Okay, so this is a powder, and then let me put it this way. It's very difficult to interpret if you are not working in lab. If you are not working in the laboratory. Okay, so this So this is the reactor. Okay, so so this is the reactor, and then we basically packed with the powder first. Let me change the color. So we first pack the powder, same volume. Okay, let's say this volume. Now what we did was, so keep in mind there are a lot of powder packed in here. Powder catalyst. Only powder catalyst is active. Keep in mind. Now we coat this monolithic with the powder, same volume. Where is it? We pack it in here. Okay, so On the left-hand side is the powder fully packed. Okay, it's the same volume we packed the monolithic and coated with catalyst. So the point I try to make is on the left-hand side, the powder is much more than on the right-hand side because right-hand side majority is a foam. Keep in mind, the silicon foam is not active. All right. So now we only put the little bit of powder on the foam, but the right volume are the same. So that is why this is the powder is more active on the conversion side. But if you calculate on the hydrogen production side based on the active material, you see what's happening? Silicon coating is much better. I'm not sure I illustrated. So basically, if you correct the productivity based on active ingredient, because here's 100% active ingredient, all right? On the right-hand side, the powder or active ingredient is only a fraction because the majority volume is non-reactive silicon carbide. So if you do the correction and then calculate the production, oh, this form is much better. So we win the game. I'm going to stop here. We only have probably a couple minutes before break. Please ask questions. If you don't understand, I'm going to interpret it to you again. Do you understand what I'm saying? The two curves are important because this is the highlight. You got to use the coated catalyst because you only need a small fraction of powder to drive the reaction. Because if you correct everything based on the productivity, based on the active ingredient, this is much better than this is the non-coated. So that means you fully utilize the catalyst on the monolithic, whereas in here you do not fully utilize catalyst. Some catalyst may not be active; it's a gas that goes through, but here you fully utilize. That's why productivity is very high. So this is the reason we go to monolithic, not only for the heat transfer, not only for the pressure drop, it's also for the utilization of catalyst. Make sense? I know it's hard for you. You have to work in the laboratory to see that. If I show you in a laboratory or I bring the reactor tube to you, you can understand this two curve. This two curve is easy for me to understand, but it's very difficult if you are not working in the catalytic reaction. You have to see the tube, saying, oh, I have fully packed 100% powder. Here, the same volume, but only a little bit powder decorated on the silicon carbide. But it turns out on the right-hand side, the productivity is much higher because it's fully utilized. So anyone has any question? If you have any question, let's wait for the next session. The beginning of next session, you can ask questions, but I would leave this to the question to the next session. I want to summarize this, okay? So what's the advantage of a monolithic catalyst? Remember, your goal is you want 100% conversion, all right? So basically and also the endothermic. So basically heat transfer, all right, which is energy efficiency because you have hot spot, you don't have to heat you do not need to heat the whole body of the catalyst. So that translates into energy efficiency. And then from this two curve, you show the productivity. All right, because the productivity of monolithic based on the active ingredient or active powder is much more than the fully packed bag. Okay, and also the pressure drop is less. So this translates into the operational capability. Okay, all right. So that's several advantages. I'm summarizing here. Heat transfer, and then because you heat it and then heat transfer from inside out. What does it mean? That means you heat silicon carbide, and then the silicon carbide heat coated catalyst. So the heat transfer direction from inside out. That means the moment the ammonia decompose and the hydrogen coming out, so they will never recombine with the nitrogen. So this is really the key to drive 100% conversion, because you take advantage of fast kinetics. Okay, I'm going to stop here. I know it's lunchtime. I think we have 1 hour break. Is that right? So after 1 hour, and you come back, we will continue another session. Another session, I think I'm going to talk a little bit about the measurement of the. I think I see the struggle of the student. You may not fully understand. So we haven't talked about how we analyze the product, the ammonia. If you have a reactor, ammonia coming from here, no, hydrogen nitrogen come here. How many techniques you have to monitor the ammonia? You have a gas chromatography called GC, IPIR. You have also online analyzer. Let's go through exercise. I'm going to give you a case study. I give 5 minutes. I want to show you a good example how you calculate the ammonia conversion, because here we show the ammonia decomposition conversion. I'm going to show the other way how you show the ammonia synthesis conversion. Okay. All right. So see you in after 1 hour from now. Okay.
Yes, sir.
Okay. All right.
We'll meet after lunch, sir.
Yeah, we'll meet after lunch. I think the 1 hour from now. Yeah,
yes, sir.
It's 1 hour break. Okay. Thank
yes.
you.
Thank you, sir. Thank you.